Let us start this lecture with a thought process. Crisis is like a coin with two sides. One represents problem while other represents opportunity. Always we are get bogged down whenever we face the crisis, but crisis is a part and parcel of human life. And with this thought process, let us start this lecture and let us recall what we learnt in the last lecture. We basically looked at the carbon burning rate. In the process, we have derived a relationship for how does the diameter of a carbon particle will vary with respect to time. If you look at the relationship, what we had derived is basically d square T is equal to d naught square minus k c T, and d naught is the initial diameter of carbon particle, and Kc is a constant. We had derived that Kc is basically 8 rho g d12 by rho c ln Bc plus 1. So, keep in mind that rho g is the density of the gas, rho c is the density of carbon, and d12 is the diffusivity between the carbon and the oxygen, and Bc is your mass transfer number. Sometimes people call it as a Spalding number. And let us look at how does this d square vary with the time, and keep in mind that this d square, this relationship is known as d square law for carbon sphere, and this is also similar for the any liquid droplet sphere. If you recall that we had derived similar relationship earlier, only that Kc will be different, but the form is similar. And when we plot this d square versus time, you will see that this is your initial droplet diameter square, right. This is this one, and as the time progress, it reduces, of course, linearly, and the slope from this relationship d square law, it will be coming as 8 rho g d12 divided by rho. So, ln Bc plus 1, and keep in mind that when the droplet diameter becomes 0, right, and the time duration for complete combustion of carbon sphere is known as Tb, that is carbon sphere lifetime, because this is the time required to for burning, complete burning of carbon sphere, and this can be different depending on the various properties like rho z, Bc and other things, and this will be, we know that Bc is basically F, we know that Bc is equal to F into YO, basically it is oxidizer, and the mass fraction of oxidizer can be 1 if it is oxygen atmosphere. If it is air, it will be 0.232, and if it is varying, then it will be different. F is your basically fuel and oxidizer ratio. So, note that this d square law will be valid not only for carbon sphere, but it will be valid for other fuel particle or and metal particles. So, therefore, only thing is that properties will be changing, and so also the other parameters like diffusivity, and but however, the law will remain same. And let us look at some data which I have considered in this table. If you look at the aluminum, is of course, the density is given here, gram per centimeter cube, and Tv it is in the calculated, and this is oxygen atmosphere, and if you look at this is 0.9, and because the B oxygen is different values, and if you look at air, it is 0.26, and it takes more time whenever the air atmosphere is there, like. And if only oxygen will be there, the time required for the complete burning of the aluminum sphere is reduced. And boron, of course, it is little higher, even for oxygen 1.57 10 power to minus 5 second. This unit is in second. And if the atmosphere is air or surrounding is air, then the time is basically 6.15 10 power to minus 5 second. And if you look at the measure value is much lower, 2.03 10 power to minus 5 for air atmosphere. This is your measured value, right. Question arises why it is so. And similarly, if you look at your carbon, it takes also calculated is higher values 2.28, 1.98 when you measure, that means you conduct experiment and measure the lifetime of the carbon sphere, then it is much lower than the calculated value. And that is true also with magnesium, and of course, the experimental data is available for zirconium. If you look at no experimental data is available, but however, the calculated lifetime of zirconium particle is higher for air atmosphere as compared to oxygen, and that is true for all the cases. As I have already explained that this BC will be different for air, Y0 infinity is 0.232, whereas for oxygen atmosphere Y0 infinity is 1. So, therefore, BC for oxygen is always greater than BC of air. Therefore, even the of course, the other properties like rho g will be different and rho c is different, diffusivity will be different. Therefore, always of course, the TB for oxygen atmosphere is lower than as compared to the air, because vigorous reaction will be taking place, there is no diluents, and therefore, it is higher. And beside this, if you look at the measured values is basically smaller as compared to the calculated values, right. These values, any one of them, if you consider any one of them, then you will find this measured lifetime burning of carbon in this particular is lower as compared to calculated value. Why it is so? Because in our analysis we have considered the constant thermodynamic properties, for example, density, diffusivity, but in real situation it is not the case. So, therefore, why? Because the these properties will be varying with respect to temperature, and as the like it is calculated, the temperature will be varying. We will see little later on that temperature does vary from the fuel surface to the infinity. So, therefore, that will be affecting the properties, therefore, the measured values is always lower than the calculated values. And of course, we have done a lot of other assumption, like there is no radiation and this is a one dimensional in nature and several other things that will be also contributing for lower values of measured lifetime of the any fuel sphere. So, now if you look at the solid fuel burning, if you consider the carbon here, and this is of course the lifetime burning of this, and this is the initial diameter. You can say this is in mm, TB in second. You will find that carbon is having basically on the upper portion, and this is your kerosene, and this D naught is basically initial fuel sphere diameter. Now, if you look at this curve, you can see that for a particular initial fuel sphere of both carbon and the kerosene, if we will compare, that this is having higher values TB. That means, more time is required for carbon same initial diameter of carbon burning as compared to the same initial kerosene droplet. Why it is so? That is the question might be coming to your mind. If you compare the carbon, this is your carbon, and the oxygen will be coming from the atmosphere. Of course, the gas will be going out here, and then the oxygen molecule has to reach this surface, and then there will be some reaction will be occurring at the surface of the fuel, right. And so, oxygen has to travel a larger distance as compared to a liquid droplet, and let us say this is your kerosene droplets. Now, what will happen? The vaporization will be taking place of the kerosene will be traveling, and then so also oxygen will be traveling from other places around the and then at some surface will be formed, and this is known as flame, and here the kerosene or the fuel, like you can say fuel will be traveling and oxygen will be traveling here. So, therefore, in this kerosene droplet, the oxygen has to travel a shorter distance as compared to the carbon sphere. Therefore, the burning will be faster, and the time required for kerosene droplet of same size will take less time as compared to the same size carbon sphere. And that is the reason why it takes less time. And if you look at the coal, which is a pyrolyzing combustion, if you look at let us say this is the coal, and then what will happen, this is your coal particles, right, and to start with, and this will be char. That means, this all these gases are released from due to the devolatilization, volatilize gases are released, and then the flame will be formed because the oxygen, this is your flame, oxygen will be coming from atmosphere and then the flame is formed. So, therefore, if you look at if for the coal, this curve will be between somewhere in between, like this is your corresponding to the coal particle, because the coal particle combustion will be similar to the kerosene, because the volatilized or the pyrolyzed gas from the coal will be going away from the carbon surface to meet the oxygen to have a gas phase flame. This is a gaseous flame or gas phase flame. But if the devolatilization rate is more, then what will happen? This curve will be coming towards the kerosene. This is for higher volatilized coal particle, coal sphere. In other words, more gases will be going, so that what will happen, the flame stand of distance, I can call this distance R f. Basically flame stand of distance. If the rate of volatilization of the coal particle is higher, then the flame stand of distance will be higher. As a result, the oxygen has to move lesser distance to meet the flame, have a combustion is lower down. So, therefore, the time required for complete combustion of the coal particle will be reduced, and it may closer to the kerosene or any other liquid fuel combustion. So, therefore, that is the things what I would like to say that we can really find out from that. Why we need to find out the lifetime of a solid fuel particle or the sphere? Because of fact that when we are designing a combustors, of course, the various kinds of particle size will be there, but we can take a representative particle size and then find out the lifetime of a solid sphere, such that length of the combustors can be determined. In other words, you will have to give enough length of the combustor such that all the fuel particle will be burnt it out before it being exhausted out of the combustor. So, that is the reason why this lifetime is estimation of a carbon particle or coal particle or any other fuel particle is essential. So, by this we can also use that and design it. Now, we will be discussing about basically temperature profile, and if you look at, we are considering the carbon. Keep in mind that this is a non-pyrolyzing fuel particle, and for these purposes what we will do, we will have to basically consider the energy equation, and keep in mind that this is the oxygen will be coming from this side, this is also oxygen will be coming, and I have already explained. Okay. And to find out the temperature profile, how does the temperature vary with respect to radial direction from the surface? This is your fuel surface, from the fuel surface. So, we will have to invoke the energy equation, that which we had already derived, that is energy equation, energy conservation that is basically if you look at mass flux rate at the surface, I can write down that square r square Cp dt by dr, this is your convection term, is equal to Kg d by dr r square dt by dr. Now, we will have to integrate this equation, right. If we will integrate, if I say this is equation 1, by integrating equation 1, we can have r square, and this is a constant mass flow rate, right. So, Cp is also constant, I can take it out, and then that will be T is equal to Kg is also constant, I can get this r square dt by dr plus constant. Let us say this is equation 2. And what we will do? We will have to basically apply the boundary condition at the surface such that we can evaluate the constant C. So, at fuel surface, what is happening? If you look at the fuel surface, this is your fuel surface. So, when the oxygen will come and meet, this carbon will be reacting with the oxidizers. As a result, some of the heat will be released, right. So, the amount of heat release, if you look at what it will be, this will be at the surface m dot at S m dot S into delta S c. Delta S c is the of combustion of carbon, you can consider, and that will be equal to the amount of heat convected out. This is the gas which is convected out. So, that will be equal to the mass flux whatever it is coming out, and this is with the Cp and with certain temperature T, and minus there will be conduction. Due to conduction, this is the convection, and then there will be conduction Kg dt by dr, and this is the condition at the fuel surface. This is your fuel surface, right, consider any surface. Now, we will be using now at R, the equation 2 becomes basically m dot S r square Cpt is equal to Kg Kg r square dt by dr, right, is equal to basically plus C. Now, if you look at this is nothing but your C becomes, I can write down here that ms dash Cpt minus Kg dt by dr, I can take r square is nothing but your this much, you can say this is your 3, right, the equation 3, this is equation 3. So, that is nothing but m dot S delta S c r square, right. So, is equal to what is C. Now, then we will put this C, the equation 2, substituting the values of C in equation 2, we can have basically r square Cp T is equal to kg r square dt by dr plus m dot s delta s c r square. So, this is the thing what we got it, and let us say this is your equation 4. And we will now basically integrate this equation, that we will do in the next lecture, and see that what we are getting out of it. Thank you very much, and we will again look at this aspect in the next lecture.